Hey there and welcome. We're going to talk about two words you probably use every single day, work and energy. But here's the thing. I'm willing to bet that what a scientist means by work is completely different from what you're thinking. Let's dive in. So let me ask you something. Right now, as you're taking this in, are you working hard? I mean, maybe you're really concentrating, trying to absorb all this, or maybe you're just holding up your phone. It feels like you're putting in effort, doesn't it? It feels like work. But is it really? In our everyday world, work is pretty straightforward. Studying for a big exam, that's hard work. Trying to push a wall definitely feels like work. Just standing there holding a heavy bag of groceries, my arms are tired just thinking about it. But in the world of science, well, let's just say the rulebook is different, a lot stricter. All right, let's clear all this up. It's time to redefine what work actually means, looking at it through the eyes of a physicist. And this is where it gets kind of weird. Think about a student, let's call her Kamali, cramming for an exam for hours. She's burning through mental energy, right? A physicist would look at her and say, nope, not much work being done there. Or what about someone pushing a massive boulder with every ounce of their strength? Sweating, grunting, but the rock doesn't budge an inch. According to physics, they have done exactly zero work on that rock. Seriously, zero.
So how is that even possible? Well, it's because in science, work has nothing to do with how tired you feel. It's all about meeting two specific, absolutely essential conditions. Let's break them down.
Okay, here they are, the two golden rules of work. Rule number one, you've got to apply a force to an object. A push or a pull. Simple enough. But rule number two, and this is the big one, the object has to move. It has to actually be displaced. If it doesn't change its position, you're out of luck. So you see the takeaway here? If you're missing either one of those things, force or movement, then scientifically speaking, no work has been done. Think back to that person pushing the rock. They had the force, for sure, but displacement? Nope, the rock didn't move, so no work. It's that simple. And of course, we can boil this down to a really simple formula. Work equals the force you apply times the distance the object moves. W equals Fs. That's it. It's actually a pretty elegant little equation when you think about it. And this right here, this is a perfect textbook example of work. The baby pulls, that's the force. The toy car moves, that's the displacement. Check and check. Both conditions are met. So yup, physics would say work is absolutely being done here. Okay, but you can't really talk about work without talking about its other half, its inseparable partner, energy. So what is energy anyway? Well, in physics, the simplest way to put it is this. Energy is just the capacity to do work. If something has energy, it has what it takes to apply a force and make something else move. And this is the really important connection. Doing work is literally the act of transferring energy. When you do work on something, you're giving some of your energy to it. So the thing doing the work, that's you, loses a bit of energy. And the thing that has work done on it, it gains that energy. They're so connected, in fact, that they're both measured in the exact same unit, the joule. Now, energy can show up in all sorts of ways, but when we're talking about basic mechanics, it's super helpful to think of it in two main categories. You've got energy of motion, and then you've got energy that's just stored up, waiting for its moment. And these have names you've probably heard before: kinetic energy and potential energy. Kinetic is pretty straightforward. It's the energy of motion. If it's moving, it has kinetic energy. Potential energy is that stored energy we talked about. It's stored because of where an object is or what shape it's in, like a stretched rubber band. And kinetic energy is everywhere, right? A car zipping down the highway, a coconut falling from a tree, the wind itself. All of these things are moving, so they all have kinetic energy. And it makes sense. The faster something's going or the heavier it is, the more kinetic energy it's packing. I like to think of potential energy as the energy of what if, It's the energy coiled up in a stretched rubber band, just waiting for you to let go. It's all that water behind a dam, just sitting there, ready to rush down and spin a turbine. Or when you draw back a bow and arrow, you're loading that system with potential energy, ready to be unleashed. It's all about stored potential. So, okay, we've got moving energy and we've got stored energy, and they can switch back and forth. But how they do that is governed by one of the most fundamental, most important, and totally unbreakable rules in all of science. It's called the law of conservation of energy. And what it says is basically a core truth of our entire universe. Energy cannot be created and it cannot be destroyed. That's it. All you can do is change it from one form to another. The total amount of energy is always the same. Let's make this real. Picture you're holding a ball way up high. Right at the top, just before you let go, it's not moving. So all of its energy is potential energy, just because of its height. Then you drop it. As it falls, it starts moving faster and faster, right? That potential energy is turning into kinetic energy. And right before it smacks into the ground, it's at its maximum speed. Just about all of that stored potential energy has become energy of motion. But here is the amazing part. If you could pause time and add up the potential and kinetic energy at any point during that fall, at the very top, halfway down, or a split second before impact, the total number would be the exact same. The type of energy changes, but the total amount never ever does. It's conserved. And that leaves us with a pretty cool question to chew on. If energy is never really gone, if it just changes form, where does it all go in the end? I mean, what happens to all that kinetic energy when the ball finally hits the ground and stops? Where did the energy go? Something to think about.